And then we said that that is followed by the length of the address field in half bytes. And we are saying that the length of the field in half bytes is the length is 20 bits. When we convert that to those 20 bits to half bytes, we get 5 half bytes. Okay, so that's why our modification record begins with the M, followed by 00007, then followed by 0005. Now, someone was asking that if it is a format 3, if it is a format 3 instruction, does it mean that we have 3 half bytes? No, we are going for format 3 instruction. You remember, format 3 instruction, it does not have an address in its machine language. It has opcode, then the field is NIXBPE, and then a displacement. We don't have an address. So if it is having a displacement, that displacement will not change wherever you take the program. Okay, so wherever you take the program, if you assembled using a program counter or base, whatever, the displacement does not change. So we don't write modification records for format 3 instructions because they don't have addresses in their machine language formats. It is only format 4 which has got an address. Remember, format 4, opcode, NIXBPE, then address. Okay, so the address can change, but the displacement will not change wherever you take the program. So similarly, instructions which do not access memory, you don't write modification records for them because the modification record is about changing the address where the program is going to be loaded. So if an instruction is not accessing memory, you don't write a modification record for that. So it means that for the SICXE, it is only format 4 instructions which need modification records because it is only format 4 where you have got an address. But if it is a simple SIC, since we have got only one format which has got your code, then the address, it means that all the simple SIC instructions need modification records. Okay, so here in our program, in this program, we are saying that this is a format 4 instruction at 006. Okay, jump to subroutine error direct. So we are saying that we are going to write a modification record for that instruction, which is the M00007, then 05 half bytes. What will be the modification? Yes, please.
Yes, why are you adding those first 2 zeros? Because according to your address, it's supposed to be 0007.
Yes. But
yes, I'm asking why are you adding those 2 zeros immediately after M? Because I'm seeing it's almost like, I think,
they are
zeros.
6 digits. 1, 2, 3, 4, 5, 6. Is that right? Now the format says that 2 to 7 in the modification record should be the starting address. Is that right? So they want us to write that address in 6 digits. 2 to 7, we said we need 6 digits. So that's why we add there some extra 2 zeros at the beginning.
Yeah, okay, thank you, sir.
Okay. So I was asking that which other instruction do you think here we need modification? Because I have told you that format 3 instructions do not need modifying because they talk about a displacement, and the displacement does not change, so that displacement will not be affected wherever you relocate the program. And we say the other instructions, which are like a format 2 instructions, which do not access memory, those ones also don't need the modification records because you are not going to memory. Addresses are in memory. So we said that we end up having only format 4 instructions if it is a SIG-XE program. So I was asking, like on this screen, which you see here, which other instructions will need to be modified apart from this one, which is at 0006? Okay, the one which jumps at subroutine WRREC, which is the one at address 0013. Very good. Then which other one? Okay, maybe before we go there, can someone write the modification record for this instruction, which is at 0013? How would you write the modification record for that instruction? M00014005. That is very good. Then which other instruction we should need a modification record here? Which other instruction? (006), very good. 0026. Can someone write a modification record for that one? Very good. Okay. So those are the only instructions which we need the modification records. So now, if you are going to generate the object code for the program, because you remember the object code now is going to contain modification records, this is how it is going to look like. We have the header record, the text records, then you will write the 3 modification records here, and then finally the end record. Is that okay? Any problem? Do we continue? I don't want to leave.
Yes, we can continue.
Yeah, okay, very good. So let us continue with some other. Now we are going to continue machine independent assembler features. Now we have been talking about machine dependent assembler features. Remember, we said those are the addressing modes, the instruction formats, and then the program relocation. Now, what are the machine independent features? It means that these are also features which will change the machine language, but not because of changing the machine, but because of other reasons. So we are saying that these are features which are not related to the machine, but they are just related to the programmer's convenience and the software environment. Okay, so usually programmers can introduce some features in their programs If you are a good programmer, you can include the features which can make your program run better. Okay. But it doesn't mean that another programmer who doesn't include those features, his program will not run. Maybe you know how to, for example, economize your memory. You could write a program which is economizing the usage of memory. But another programmer who doesn't know how to do it, how to minimize the amount of memory used, his program will also run, but you will realize that you will be having different codes. Okay, someone will introduce new features in the program, which will maybe make him get what he wants. So here, we are also going to get different machine language instructions, not because of the program, sorry, not because of the machine, but because of the what? Convenience of the programmer or the software environment. Okay. Now the same program has been written and some features have been added there. Okay. So the first machine independent feature we are going to look at is what we call the literals. Literals. Okay. Now, a literal is defined as a constant operand, which is written as part of the instruction which uses the operand. Okay. It is an instruction which writes the operand in the instruction. The operand is written in the instruction. Okay, so they are giving an instruction, like there is a literal here. If you can see this instruction, which is at 001A, load the accumulator with the characters EOF. So there are those characters EOF which we are going to load into the accumulator. So the information you need, the characters you want to load are within the instruction. They are within the instruction. It is something like immediate operand. Like you can see here where you say, load the accumulator with the 3. So it is not an address. What you want to put into the accumulator is a 3. It is not the same thing as someone saying load the accumulator with the length. Because here when you say load the accumulator with the length, you need to go to memory, find out what is in memory location in length, and that is what you will put into the accumulator. But if I know what to put into the accumulator, you can say load the accumulator with a 3, okay? Or you can say load the accumulator with the characters EOF. So when I write this one is a literal. So that is how we write a literal. An operand which is written in the instruction which is using it without using an address, okay? So a literal is an operand which is written as a part of the instruction which uses that operand. So like this one, load the accumulator with the characters EOF. This one specifies a 3-byte operand. The operand is EOF, okay, which we are going to load into the accumulator. There is another literal at 1062 which says test device at 1062. Okay, this one, 1062 test device. You see how we write the literal. You put equal signs, and then if it is a hexadecimal number, you write X, and then you mention the number. The same thing here, write device. You put equal signs, and then you write the hexadecimal number. If it is a character like here, you put equal signs, and then you say characters, and then you mention the characters in that string. So literals They are constant operands which are written in the instruction, which is using that literal. Okay. For example, load the accumulator with the characters E or F. That one specifies a 3-byte operand. Okay. E or F, those are 3 bytes. So that specifies a 3-byte operand whose value are the character string E or F. Then this one, test device hexadecimal 05. It specifies a 1-byte literal with a hexadecimal value 05. Now, literals are different from immediate data or immediate addressing. So let us look at this program. Okay. Let us look at this program clearly. So we are saying that at 001A, load the accumulator with the characters E or F. This is a literal. But at 0020, we have loaded the accumulator with the 3. This one is immediate operand. So in both cases, what you are loading into the accumulator is given in the operand side, but the difference is in assembling. For immediate data, for immediate addressing, the operand is assembled as a part of the instruction, which means that the operand appears in the machine language. For example, here load the accumulator with a 3. A 3 you see is here, 003, it is there. This one which says compare the accumulator with the 0 is somewhere here in the machine operand. So the machine instruction has got the operand if it is immediate addressing. However, for a literal, E or F is not found here. You don't see E or F in the machine language instruction. Okay. Similarly, this other instruction, which we said is also literal, like a test device hexadecimal 05, within the machine language, you don't see the 05 there. So that is the difference between literals and the immediate operands. With the immediate operands, the operand is assembled as a part of the machine language instruction, which means that the operand appears in the machine language instruction. But if a literal, the literal is at some other location, and we assemble again, calculating the displacement like other format 3 instructions. Okay. So if you look at this instruction, for example, okay, if you look at this instruction, which says load the accumulator with the characters E or F, E or F is found, characters E or F is found at another address, like here 002D. That's where you find the characters E or F. So to translate this instruction, you need to calculate the displacement using program counter or base addressing like we did. And then we fill in the other fields. But if it is immediate addressing, the immediate operand is what you have in the machine language instruction. Yeah. So that is what we mean there, that with the immediate addressing, the operand is assembled as a part of the machine language instruction. But with the literal, the assembler generates a specified value as a constant at some other memory location. Okay. Now, if you have literals in a program, they are usually put at the bottom of a program in an area we call a literal pool. So all literals are gathered in a literal pool, usually at the bottom of the program. But sometimes, because this is the convenience of the programmer, Other times, you can put the literals anywhere in the program, wherever you want them. You can put them anywhere. But if you are going to put them in any other place which is not at the bottom of the program, you need to use that directive, which is called literal origin, LTORG, literal origin. So when the assembler encounters that operand literal origin, then it creates an assembler pool and a literal pool immediately below it. Okay, if I can repeat, I'm saying that literals are usually found at the bottom of the program, but the programmer can decide to put literals anywhere in the program so long as you use that directive LTORG. So when the assembler finds LTORG, then it will generate literals immediately below that directive. Okay. Now, all literals are found into what we call a literal pool, a literal table. During pass 1, when you are generating a symbol table, a literal table is also generated for a program which has got literals. So a literal table is a table which contains literals. Now in the literal table, you will find the name of the literal, the value of that literal, and the address where it is found. Okay. So like in our case, if we look at this program, in the literal pool, we are going to have a literal. Here we have got a literal character as EOF. So the name of the literal is EOF. Its value is 4546. That is the value of the literal. And then the address where it is found is 002D. Okay, is that clear?
Yes, sir.
Okay, then you can put a second entry in that table, because we have this other literal here at 1076, hexadecimal character 05. So that one is also literal. So the name of the literal is 05. Its machine language instruction. Sorry, its machine language equivalent is 05. And then the address where it is found is 1076. So those are entries in the literal table. Okay. Okay, any question there? We are looking at machine-independent assembler features. So do we continue?
Yes, we can.
Okay. Now, another machine-independent feature is what we call symbols, symbol-defining statements. A programmer can use symbols or symbol-defining statements by using that directive, which is called equate, EQU. This one allows a programmer to define symbols and specify their values so that subsequently you just mention those symbols. Okay? Like for example, in a high-level language, you can define a constant and give its value at the beginning. Yeah? So you can call it mark, and use, for example, you say mark is a constant. Let me say 30. So that when you are somewhere in the program, you can say 20 plus mark, so long as it has already been defined to be a what? To be a 30. So you can use it for other expressions. Okay. So it is the same thing here. How do we define constants in a high level language like what? Like a C. How do you define a constant? No idea? Hello? Hello?
Hello?
No idea, you don't know, you don't know how you define a constant in a high level language like a C or something? Okay, yeah, very correct. You use that define. So you can say define and then maybe you name the name of the constant. Okay, using the constant. Very good. I think that is what you do. Okay, and then you can name it and then you give it. You name it and then you give it a value. Okay, so that is what we do here. So, for example, here we define, you write the symbol. For example, you can say mark, and then I say mark, I equate 50. So that wherever you find the word mark, it will always be evaluated to a what? To 50. So this symbol has to be entered into sim tab. It has to be entered into sim tab with its value. Okay, very good. I think that's how you do it. You say hash define a const, and then you give the value. Okay, so here we just say you put the symbol, and then you write EQU, and then you put a value for that symbol. Okay. So they are giving an example that, for example, if you had for an instruction like a load register T with that immediate data 4096, okay? So if you are going to be using it very often, you can use a symbol and you say, for example, max len equate 4096. So that subsequently, instead of writing 4096, you can use the symbol which was defined to be 4096. So that you can now write load register T with max len. Instead of writing load register T with immediate 4096, okay, you can equate 4096 to a symbol, and then you can use the symbol in the subsequent instructions. Okay. Another symbol is the ORG, which means the origin. Okay. Now, this one is mostly used like to reset the program. It is like used to reset a program. So if you have got your program, let me give an example. Suppose you have begun from address 0000, then you go 003, 006, maybe 009. Someone who can say ORG 3000. Okay, so that means that change that addressing scheme so that instead of continuing with that sequence, now begin from 3000. So when you put that ORG, it will reset the location counter to that given value. That means you will begin now counting from that value. you forget the sequence you have been following from behind, and then you begin a new sequence beginning from that below that address which has been given. Is that okay? Is it fine?
Yes, it's fine.
Okay. I beg that we stop here. I don't know. I feel very tired. I don't know why, but I beg that we stop here and we continue from there next time. Now, we had said that next time is a Friday. Some people had requested that we can have 2 lectures, one in the morning and another one maybe in the afternoon. How early did you want the morning lecture? Because I have found myself, I may not be able to. I have got an engagement in the afternoon, which wasn't anticipated. But how early do you want this one for Tuesday, the morning one? Can we have it at 8? Is it possible? Hello? Or you are occupied? If it is not possible, I think we can, 10 will be a bit late for me. So if we can't have it at 8, then we will find some other time next week. Okay? So if it is 10, let us have it next week. Someone is saying, I didn't send the recordings last time for the previous lecture. I think I did. Didn't I?
No, we are still waiting for them.
Hey. Okay. Maybe I will send them. I will send them alongside these ones. But I remember I tried, I don't know what happened. I tried and maybe I gave up. Let me try again. So if we can't have some time, how about Saturday? Are you very busy on Saturdays?
Sir, maybe not Saturday.
Okay, so if we can't make it then let us find some time next week. Okay, let us find some time next week then. Okay, have a good morning, everybody. Let us stop here.